Anyway, so I'm talking about white dwarfs. Some people study really exotic objects like a black hole. I mainly study white dwarfs, which are not quite as exotic, but I hope to convey to you that it's still very exciting and exotic enough. So what is a white dwarf? Many of you may have heard of a chart diagram or Hertzsprung-Russell diagram. Do we have a pointer somewhere? This? Okay, good. So if you plot the color of a star, which is related to the temperature of a star, against brightness, many stars line up on this line, diagonal line, hot and bright, cool and faint. This is called the main sequence. And I think Bob is going to talk a little bit more about this after my talk. Our sun is on this main sequence somewhere. But I think around 1900, maybe slightly earlier, astronomers discovered a faint companion star to Sirius. So Sirius is one of the brightest stars in the night sky, the brightest, except for the sun, in the constellation Canis Majoris. And if you can see, well, this is an optical image of the Sirius itself and a faint star to the lower right. It seems to have the same kind of color as Sirius, looks white to our eyes. So it's supposed to have the same kind of temperature, but it's much fainter. So if the temperature is the same, but it's faint, that means the star is much smaller than Sirius itself. And that's why it's called white dwarf. White is the color, dwarf means size is small compared to normal stars. This is actually an X-ray image in which this white dwarf is much brighter than the normal star Sirius. So that's how observers discovered white dwarfs. What is our understanding? And I hope Bob will explain it in more detail. But white dwarfs are what stars like our sun will end up as. By the end of its lifetime, the sun will have used up all the hydrogen in its core. When that happens, it expels the outer layers, and that becomes what we call planetary nebula. It has nothing to do with planets, but to some astronomers, this kind of image looked like the disk of a planet, and leaves behind a white dwarf. It's the burnt out ash of a sun-like star. More massive stars end up as a supernova, explode, and leaves behind more exotic objects like neutron stars and black holes. But white dwarfs have almost the same mass as our sun, but its size is about the same as the Earth. And the sun has a diameter about 100 times bigger than the Earth. So it's a very dense object. Let's see, I had to look this up, but a sugar cube-sized white dwarf material will weigh as much as 3 Cadillac Escalades, so 3 big SUVs. It's very dense. Neutron stars are even denser, but we won't go into that today.
About that this morning.
Okay, so you heard about that this morning, that's good. Mm-hmm. So, according to the theorists, sun will end up with a white dwarf like this, in which the core is mostly made of carbon and oxygen, which are the ashes when you burn hydrogen to helium and then helium to carbon and oxygen. There's a layer of helium and maybe some layer of hydrogen. So how is the size of the white dwarf determined? So it has to be able to support its own weight it needs some sort of pressure. And I'm not going to get into the details, but it's basically electrons in the atoms pushing against each other, which means if you do the calculations, if you have a more massive white dwarf, it becomes smaller because the pressure due to the weight is greater, but the pressure due to electrons pushing against each other is about the same for the same density. You have to make it denser to be able for a white dwarf to support its own weight. So if the mass is about half of our sun, the size is maybe slightly bigger than the Earth. More massive white dwarfs can be smaller than that, smaller than the Earth. In contrast, normal stars are supported by the pressure because the temperature of the gas is high, which is because of the nuclear fusion in its core. Nuclear fusion happens because the pressure is high and the temperature is high. It's sort of circular, but it keeps the star in equilibrium. So that's the story when a white dwarf is isolated from everything else. But sometimes you have a binary star system. In this illustration, this blue dot here is a white dwarf star, the size of the Earth. The entire system, it's about the size of the Earth-Moon system, maybe slightly bigger, maybe slightly smaller. In this case, the white dwarf is sitting very close to a more or less normal star. Because of the tidal force of the white dwarf, this normal star is losing mass. And because the binary system is rotating, the matter cannot fall directly onto the white dwarf, but it swirls around, like the water going out of a sink from a bathtub. But because of the orbital motion of the binary, there is a definite pattern to this, which we call accretion disk. Accretion means the white dwarf is getting mass from the companion star. The disk shape, because everything stays in the orbital plane of the binary. And this accretion disk, because matter is falling onto the white dwarf, is heating up and gives out light. And often this disk can outshine the white dwarf, the normal star combined. So that's the kind of binary I study often. Yes, question?
How's the distance between these two stars vary in time? I mean, when that white dwarf was a red giant,
yes.
Was that other star still about the same distance inside the red giant, or was?
Yes. What happens? It starts off somewhat farther apart, maybe Sun-Earth distance. When it becomes a red giant, the normal star is buried inside the thin atmosphere of the red giant. Because of the friction, it sort of spirals in. When the white dwarf is left behind, it can be a much smaller binary. That's a very good question, but advanced. Anyway, so accretion itself is a powerful energy source, and I study binaries powered by accretion. But another thing accretion does is that it gives the white dwarf hydrogen-rich matter, which is fuel for nuclear reaction. And sometimes that white dwarf becomes a nuclear bomb in essence. So white dwarf is the ash, nuclear ash of a sun-like star. You dump a bunch of hydrogen on the surface. It can start runaway nuclear fusion on the surface and becomes a nova or classical nova. This is an animated GIF showing two images of a star field. This star was much, much fainter in one image, and much brighter. This star seems to be changing too, but you can see in both frames there is a notable star. This star didn't have any noticeable star beforehand. So these are called novae. Nova means new in Latin because some ancient observers thought these were new stars because they saw a star where none was known before. And this is a light curve, so this is time from April 21st to early June. This is magnitude, this funny unit that astronomers use to measure the brightness of a star. This is the same nova that happened in April of this year. It was as bright as 8.5 magnitude. It's down below 15, which is a factor of about, let's see, 200, 300 fainter, and it might become fainter still. So there are maybe about 30 such nova events per year in our galaxy, but because sometimes it's too close to the sun, we only discover 8, 9, 10 per year. By the way, many novae are discovered by amateur astronomers, people who watch the sky as a hobby, because professional telescopes tend to study a very small field, very deep. Amateur astronomers survey the entire sky many times every few nights. So they're very good at discovering these kind of unpredictable events. So this is a classical nova, and as I said, that's a nuclear explosion on the surface of a white dwarf. And some of the researchers who study classical nova work at Los Alamos National Laboratory, for example. So there is a connection between studies of these kind of nuclear bombs and the weapon kind of nuclear bombs, although I never crossed the boundary to weapons. One interesting thing, accretion, as I said, is an energy source and a fuel source, but also a source of mass for the white dwarf. So it's like the white dwarf is eating and gaining weight over many, many thousands of years. But when the explosion happens, it expels most of the accreted matter because nuclear fusion generates so much energy. So it's like a binge and purge cycle. Big question among researchers today is whether white dwarfs gain mass over time, or gain weight, or actually lose mass. Because when you study the expelled matter from the nova explosion, we find hints of matter that must have come from the inside of the white dwarf. So the explosion is so violent, it's expelling part of the white dwarf, not just the hydrogen-rich fuel that it accreted. So until a few years ago, the conventional wisdom in the field was that maybe white dwarfs stay at about the same mass after many cycles of binge and purge, as I put it in this view graph. So accretion gaining mass for maybe 100,000 years, classical nova explosion, which lasts for a few months, which expels all the matter more or less, and the white dwarf stays at about the same mass. But maybe that's not always the case. Maybe the white dwarf can gain weight over many binge and purge cycles. Why do we care about the long-term weight gain of a white dwarf? Because there's a limit to how massive a white dwarf can be. It's called Chandrasekhar limit. It's essentially the limit of how high a pressure the electrons bashing against each other in the white dwarf can create. So if your white dwarf becomes more massive than this limit, maybe 1.5 times the mass of the sun, the white dwarf can no longer support its own weight. It has to do something. Does this work? One possibility is accretion-induced collapse, which is a technical term, but it's essentially an implosion. This video is of a controlled implosion of a building that somebody wanted to demolish. Of course, there are some debris thrown off by that implosion, but most of the matter falls back onto its own foundation. That might happen, and that's what we call accretion-induced collapse. But because it's implosion, it's not very spectacular. We haven't caused any accretion-induced collapse in its act. The other possibility is that a special type of supernova, type 1a supernova. So what happens in this case is that as the pressure builds up inside the white dwarf, carbon and oxygen starts runaway nuclear fusion, even though it's nuclear ash in the case of sun-like stars. Then the entire star can explode as a gigantic nuclear bomb, much bigger than classical nova, and destroy itself. It will leave nothing behind, it's just expelled. The entire white dwarf mass is expelled. And we've known such type 1a supernovae for many years, and I think we've recognized that as a class since maybe the 1930s. And it can outshine an entire galaxy consisting of hundreds of billions of stars. This is an example from last year in a nearby galaxy called Messier 101. There was nothing in this position. Now there is a bright star. And this was called supernova 2011 FE. You may have noticed astronomers often use boring names. FE, I think they use 2 letters of the alphabet because there are about, well, 200 or 300 each year. So by using 2 letters, you can name them all. So this is an example of a recent type 1s supernova. And it's not obvious from this figure, but such a supernova can become brighter than an entire galaxy normally is. What happens? So let's see. I said classical novae probably happen maybe 30 times a year in our own galaxy. Type 1s supernova probably happen maybe 2 or 3 times per 1,000 years in our galaxy. One famous example was observed by the famous Dutch astronomer Tycho Brahe in 1572. So that's 450 years ago or so. Today, we see a hot gas expelled by that explosion in the X-rays. This is a Chandra X-ray image. But however carefully you look, you won't find any remnant star in the middle. So that's one way we know that the entire star was destroyed. Although, I'll come back to the question of binary companion. I'm going to skip 2 view graphs to do with cosmology. If you have questions, I can answer some. But essentially, these supernovae are so bright, you can observe them in the distant universe. And that's being used to study the expansion history of the universe. Anyway, how to make type 1s supernovae. So it has to be a white dwarf that's gaining mass or rapidly gains mass. So it needs a companion star. One way to do it is that binary star system that I showed you before, the kind that creates nova explosions. It has a white dwarf and a relatively normal star nearby. Another possibility is that there may be binary stars of two white dwarf stars. Under certain conditions, they can spiral in, merge, and then explode. So, as I mentioned, we don't know whether these CVs can actually increase the mass of the white dwarf. That's why we'd like to know a little bit more about how much mass is gained in the accretion phase and how much is actually expelled in classical novae. Because if white dwarfs can gain mass reliably, then it makes it likely that some type 1s supernovae come from CVs. But type 1s supernovae are rare in any given galaxy. During explosions, they're so bright you can observe distant ones, but before the explosion, they're faint, so nobody knows what the systems were like. So that gives us a problem in terms of understanding the origin of type 1s supernovae. We can't really observe the supernova before it explodes. So we have to do some indirect studies. One type of study is to look for the companion stars that may have been left behind. So people have looked at the Tycho supernova remnant to see if it was a white dwarf and a normal star, can we identify the normal star that may have been left behind? That kind of studies have never found a convincing evidence for the binary companion, but I think this kind of study will get better. Another indirect study we can do is to look at where in a galaxy type 1s supernovae tend to happen. That gives you some hint of the likely environment that these binaries are in, and we think binary white dwarfs tend to live in certain place like a spiral arm. CVs tend to be much older, so it's scattered all over the place, that kind of thing. So that's the kind of study I'm involved in. And even though I skipped, it's important because some people, many groups actually are using type 1s supernovae to study the expansion history of the universe, which actually won the Nobel Prize last year for physics. To conclude, and I'd be happy to take a few questions if you have any. White dwarfs turns out to be rather common in the universe because there are more sun-like stars than very massive stars. Even though they are nuclear ashes, many white dwarfs are in binary star systems, which can create spectacular fireworks, classical novae, and type 1s supernovae. My own research is on CVs, which is powered by accretion and by explosion. I'd like to know how many such stars there are in the galaxy. We only have numbers accurate to maybe a factor of 30. I'd like to make the number more precise. How massive are the white dwarfs in these binaries today, and is it growing or shrinking? If it's growing, will it end its life as accretion-induced collapse or implosion or type 1a supernova explosion. And I guess our dream is to find a system that will explode as type 1a supernova within our lifetime or research lifetime. Hopefully not in our own galaxy because that could be too dangerous, but maybe in nearby galaxy. That would be really cool if we can study a binary system now, and 20 years later it explodes as a type 1a supernova. Nothing could be more spectacular than that if you're studying this kind of binary systems. So I'll stop here. Thank you very much, and I'll take any questions.